We are very glad to be here to represent the team to talk about telematics data and how we use machine learning, in particular XGBoost, to mine telematics data and derive insights. So before we dive into that, I want to give you guys a brief overview of our team and the safety products we have built throughout the years. So when we started the year of 2018, Dara, the CEO of the company, announced that the top priority of the company is to stand for safety. So throughout the year, we had the clear mission to become the industry leader on safety and make Uber the safest transportation platform. So we have made a significant progress since then, building a multitude of safety product features. We have also launched lots of products focusing on driving safety. In an effort to reduce drowsy driving, we have introduced the driving hour limits, which puts a time limit on how long the driver can drive on the Uber platform before taking a break. Speed limit alert, which helps the driver to keep track of the traveling speed and the posted speed limit. And also to reduce phone-related distracted driving, we introduced the phone mount alert, which encourages the driver to mount the phone throughout the trip and reduce the amount of handling while driving. And recently, Ride Check, which automatically detects whether a trip has a potential crash or not. And our safety response team will proactively reach out to make sure everybody gets the help they need if that's the case. So these are some really awesome products that we have built, most of which actually are powered by solutions based on telematics, which is our topic of today. So what is telematics? In general, it's a service that uses telecommunication to transfer data collected from sensors such as vehicles or smart things. So it falls into this general domain of Internet of Things. Our major interest here is vehicle telematics, which concerns the use of sensor data to understand how, where, and when the vehicle operates on the road. In general, there are two solutions to do this. One is to install sensor devices to the vehicle itself. It ranges from installing some simple dongle devices to installing very advanced sensors, like in autonomous driving cars. In general, installing sensor devices to vehicles is not a very scalable solution. A second solution is to use smartphones, which have tons of sensors and also offer very convenient ways to transfer data using Wi-Fi and the 4G network. So compared to installing sensor devices to vehicle, smartphones are widely available. They are relatively cheap, and they have a very short upgrade cycle. On the other hand, their quality of the sensor are generally very low, and they only measure the motion of a phone. And in order to derive a motion of the vehicle, we have to do tons of signal processing. So the rest of the talk is gonna be focusing on solutions based on smartphones. There are lots of potential applications of smartphone-based telematics. Some I list here, for example, classify passenger versus driver, the detection of the transportation mode, the activity, identify whether the driver is handling the phone or the phone has been mounted, deriving driving events such as speeding, acceleration, brake, stop, turn, etc., and understanding road conditions, for example, potholes, speed bumps, etc. So there are two types of sensor data that we commonly use in telematics analysis. One is GPS, which measures the absolute location, velocity, and the time of the phone. So it's generally collected at a very low frequency, less than 1 point per second. Second type of sensor is IMU, which stands for inertial movement unit, which measures the relative motion of the phone. It typically has a accelerometer unit, which measures the three-dimensional linear acceleration of the phone, and sometimes a gyroscope, which measures the three-dimensional angular velocity of the phone. Compared to GPS, it's generally collected at a much higher frequency, sometimes more than 20 points per second. The plot on the right here shows some readings from GPS speed, the 3-axis from IMU accelerometer, 3-axis from IMU gyroscope. As we can see here, the data from IMU is collected at a much higher frequency, but compared to GPS, it's also more noisy. So most of the raw sensor data we collect are very noisy. We need to apply signal processing and statistical inference to denoise the data before we generate more meaningful events. This is where we collaborate a lot with our partner teams like Maps and Sensing and Perception. We leverage some of their work here. One type of pre-processing we commonly do is GPS map matching. This is because GPS data is often provided with a certain accuracy due to signal blockades, satellite geometry, etc. So each reading from the GPS has horizontal accuracy, which means that the true underlying unknown location is within a distance from the given point. Because of this, sometimes the GPS traces do not fall into the underlying road network. For example, here the black dots are from the raw GPS trace. In order to fix this, we apply map matching to process the raw GPS, which snaps the raw GPS to the underlying road network. Map matched GPS is supposed to be much more accurate in terms of both the location and the traveling direction. A second type of pre-processing deals with the phone to vehicle orientation. This is very important for using IMU data because the reading from IMU depends on actually how the phone is oriented. A slight change of the phone orientation will result in very different readings. To illustrate this, I have an example here where we just rotated the phone twice, 45 degree, 90 degree clockwise, around the z-axis. Although the underlying vehicle hasn't moved yet, we see the readings after the rotations are very different from the original ones. So in order to use the IMU data from phone to make inference about the vehicle movement, we have to estimate how the phone is oriented relative to the vehicle and properly align the phone back to the vehicle frame to make inference. So after proper pre-processing, we can derive meaningful events or features. One such example is a long stop, a sudden long stop after while driving. We do this by looking at the GPS data. The plot on the left shows the GPS speed over the course of a trip, where you can see the speed is almost 0 for a long time there. This is our stop event. A stop could be an indication of a car crash, a car mechanical issue, but it also could be because the driver just wants to take a coffee break. Oftentimes, it is very useful to get more information from other data sources, such as maps, to get more context about the stop event. In the middle plot here, we show 2 long stops that are not auto crashes. One of them is at 7-Eleven, where the driver just stopped to go to the convenience store. The other is at a gas station, where the driver just stopped to get some gas. Compare this to the plot on the right, where we also plotted the long stop by road class. In that case, a long stop on the highway is supposedly to be more likely to be a car crash or a flat tire compared to a long stop on local streets. So this type of information from map can really give us more context and help us understand what's going on. So these are some examples where we build features manually by looking at the patterns in the data, and we iterate and finally, refine the process of defining those features. In the context of dealing with the sensor data, which is, high frequency, noisy, has this challenge of rotation, a dependency, and lots of like a dependency, interactions among different series. It is actually very helpful to leverage deep learning for automatic feature engineering. For example, we can build a LSTM model on all time series from the sensor data and extract the sensor embeddings to summarize all the information from the sensor data that is relevant to event of interest. Here is an example architecture where at the bottom layer we have the raw sensor data. Because sensor data is so high frequency and large, we oftentimes run some dimension reduction, just extract some basic features to reduce the time steps we build off the graph. And we feed this summarized feature into like a multi-layer LSTM, run the model through, and use the information from the last hidden layer as our sensor embedding to summarize the information that is relevant to a certain event. So before I hand over to Gorkem, I want to briefly talk about our model development pipeline. This is very important to the type of work we are doing because we're dealing with petabytes of data. We need a very efficient pipeline for us to build the models quickly and iterate. So we have two separate pipelines. One is for non-deep learning, where we store the data in Hive and then build some features using Spark. And then we build our machine learning model using XGBoost and the Spark ML transformers, all within Spark. So we build the model on millions of trips, millions of records, and also validated the model on millions of records. So after finalizing the model, we save the whole pipeline, which can be loaded directly into a new Spark session to score new trips. So for the deep learning pipeline, we follow a similar process. We store the data on Hive, and then we use Spark to compute some basic features. Then we save the TF record file format, which is required by which can be loaded directly into TensorFlow to train the LSTM model. We finish the training and then save the pocket buffer back to Spark. Spark, there's some memory dependency there, which allows you to run TensorFlow model directly in Spark to score new trips. So here we run the LSTM model, generate the sensor embedding, which we use as additional features in XGBoost. And this allows us to kind of disentangle this two-step. We can iterate much faster. Now, I'll hand over to Gorkem to talk more about how we use XGBoost.
Thanks, Wayne. So now I'd like to go into some more modeling details and about XGBoost. So to start, I'd like to briefly quote from XGBoost website what XGBoost is. So it's an optimized, efficient, flexible, and portable machine learning library. So it implements machine learning algorithms based on the gradient boosting framework, and it provides parallel tree boosting that solve many data science problems in a fast and accurate way. So in short, when you have a problem, your data is structured and your response variable is not high dimensional, like could be classification with low number of classes, could be regression, could be binary classification, and you care about performance, like model accuracy, and you don't care that much about interpretability, then XGBoost is the state of the art that you probably would like to go with. So XGBoost at Uber, so we at Uber heavily utilize it, and so there are multiple projects that XGBoost is based on. One particular example that I'm personally involved in is the ride check application, which we announced last September. So the goal is when something goes wrong during your trip, such a car crash, which is a rare event, like very, very rare event, but it also occurs, we'd like to detect it as early as possible and then proactively reach out and so improve the situation. So essentially it's a binary classification problem, works at the trip level, and the response is one of the two categories, 0, not crash, majority, and 1 is the cases where there's a crash. So simply the scale of the data at Uber, so there are billions of trips. We passed the 10 billion mark, 10 billion trips. For each trip, Uber is collecting sensor data from the driver's phone. So millions of trips every day, terabytes of data, sensor data each day, and petabytes of data annually. And so this data is for later analysis stored on HDFS and analyzed with Apache Spark and Hive, Apache Hive most commonly. And so in analyzing this data and building models with XGBoost, we have several options. One is the Michelangelo platform. It's an internal machine learning platform, machine learning as a service platform. So then distributed XGBoost is available as one of the options to train your models. Also, it allows you real-time model serving for later deployment. And it comes with diagnostic dashboards. You can monitor the model's performance, day-to-day performance, or during model development, it allows you to see feature importances. It also has a shared feature store, like different departments, different teams of Uber can contribute to that. And one feature might be used at a different team's project. Another option is more commonly used one, like universally, the interactive shells, interactive environments. We can directly use Spark Shell. We commonly use the Scala interface, the Scala API of Spark. Also, there's the notebook environments. There's Spark Magic and Apache Tori kernels in particular that support the Scala API of Spark. And there's Data Science Workbench, another internal tool that allows you to launch Jupyter notebooks, again supporting the Spark Magic kernel, so that you can use the Scala API or also as well as the PySpark API. And whenever you need an external dependency such as XGBoost, which is now available on Maven, you simply specify the name of the package, and then it's gonna be available in your notebook. So that's another way to use XGBoost and train your models. And the third way is the single machine way. So with large scale data, it's not possible to train your models on a single machine. But once the model is trained, you can serialize and load it into a single machine for further, more fine-tuned analysis, or scoring a small number of trips, for instance. So that's another option. Also, typically XGBoost development first happens. The R and Python API may come first for if there's a new feature. So that's another reason you may want to use the Python API or the R API. But typically for large scale, Python and R is not an option. So for training on large scale data or predicting inference on large scale, you have to go with the Java, Java port. And then for fine-tuned analysis on small scale, Python and R can be a better choice. So now I'd like to compare two models, basically. So the reason I'm just comparing this is for the right check, we had two phases. One was initially used Spark ML, random forest. And then second phase, we switched over to distributed XGBoost Spark. So basically, random forest, the traditional random forest algorithm, both algorithms are tree-based. In random forest, the trees are trained in parallel, totally independent of each other. Whereas in XGBoost, each new tree depends on the previous trees and kind of tries to minimize the error made by the previous tree ensemble. In our experience with Spark ML random forest, going beyond 50 trees it made no difference to performance. But XGBoost, we can go as large as 1,000 trees and see the benefit of it. So the implementation SparkML is dependent on the traditional MapReduce, Spark MapReduce, which was not designed in the first place for machine learning, whereas the distributed XGBoost is all reduced based, which is much more efficient for iterative machine learning algorithms. So, and I'd like to mention one detail. Actually, now helped us a lot in this optimization. So there are two forms of optimization, two forms of parallelism built into XGBoost 4J, the distributed XGBoost. One is the one that's based on OpenMP. So OpenMP, in the original XGBoost, it's used for splitting the job into multiple cores. And when we switch over to XGBoost 4J and we go with the default settings, the OpenMP layer is not utilized. So the distribution into the multiple cores in a single node is also obtained by Spark parallelism based on Spark. But once we turned on the OpenMP setting, we gained up to 50% faster training speed. And if you want to enable it, once in the XGBoost options, you'd set the number of n thread to a larger number, optimally the number of cores in one single node of your cluster. But you also change one of the Spark settings. It's Spark task CPUs into the same exact number that you set for n thread. So another note is about the feature importance. So in XGBoost and many other tree-based algorithms gives you the importance of features. So typically, although these models are not interpretable, this gives you a crude idea of how these features are utilized and which one is utilized more. So in XGBoost 4J, the default setting is frequency, named frequency. Basically, whenever a feature is used in a single split, it increments the count 1. But there are cases where this metric might not be the best one. And my personal observation is when it's a categorical variable, like low number of distinct levels, then the importance turn out to be very low, whereas the pure noise might beat it in terms of this importance because it has much more potential to create splits, even though it's a spurious split. So far, as I mentioned, this was one reason I was transferring my models to Python, serializing and loading it to Python and R, because there are other options available there. But none informed me as of version 0.82 in the Java port. Java version is also going to have these alternative metrics of feature importance, such as gain and total gain. So to summarize some takeaways, as I mentioned, feature importances can be misleading. Actually, whichever form it is, there can be some artificial examples can be constructed that it's not very reliable. So I think it's best if you want to get an idea, make a decision about removing a feature, the best is to remove that feature and train the model again to see if its impact is high. So another one, adding more negative examples in a binary classification class can help a lot. I mean, what I mean is, you may think that if your case is highly unbalanced, you don't need much of the negative examples and you go with a small subsample of it to reduce the training data size. But my experience is add as much as try to saturate it by adding all the negative examples available to you too until performance no longer increases. So another one is the need to be careful when you process your negative and positive examples separately. Ideally, all of the examples, irrespective of the label, should be processed together. But once this is not the case, there's a lot of room for accidental leakage. So it can be challenging when you're transferring your development system to production. There'll always be discrepancies, small details, small bugs, and carefully designed tests need to be done. And finally, again, about XGBoost 4J. So XGBoost, there are two kind of feature vectors in Spark. One is the sparse version, which treats doesn't feed all the zeros with actual zeros, only feeds the non-zero elements. The other one is the dense vector, and XGBoost gives you no warning if you train your data with sparse vectors and then feed a dense vector during inference time. But actually, it's quite different in terms of the model size, because like in zeros in a sparse vector are treated the same as missing values, whereas in the dense vector, zeros are actual zeros, so they go into totally different tree branches, which results in different predictions. So, yeah, thank you.